tricky situation for us to tackle. But in some cases, that works fine. And also, they don't want to turn the whole internet off, but they don't mind a lot of collateral damage. Maybe there's a blog spot thing that they really don't like. So they turn off all 20,000 blog spots. They don't mind, hey, they're just blogs, whatever. Okay, so there are a couple of different attacks that we've actually seen in the wild from these filtering or censorship systems. Probably the big three are, they have a list of IP addresses and ports that they try to block, and they do keyword searching in TCP packets. So if you have democracy or Falun or something like that, then they look for these little substrings, and as soon as they see a TCP packet with that substring, then they send reset packets in both directions and try to break the connection. And then also they intercept DNS requests and they send you to a different page. And that page says, hey, it looks like you're trying to access censored material. I think you might be a bad person. Maybe you should consider reforming, or whatever the page happens to say. And that tends to work also. Okay, so a lot of design assumptions that we want to think about here. One of them is the network firewall has limited CPU and memory per connection. It's not like you can sit down and say, okay, let's do some statistical analysis and let's try to break the crypto here and make sure that you're obeying the protocol perfectly for every single person in one of these countries connecting out. All they can do is look at it in a cursory way and say, okay, that kind of looks like SSL, or hey, look, I know where that connection's going to, I'm going to block it. So we don't need full steganography, which is useful because I think it's impossible. But that's also something we can get into afterwards. And also, we might assume that there's a time lag between attackers sharing notes. Maybe a certain country figures out how to filter some system, but the next countries don't figure it out for quite a while afterwards. And then maybe the exception to that is a company like Cisco, where they say, we have developed a new innovation. This new tool will let you oppress your citizens better, and we're going to sell it to every country who wants to buy it. So that's maybe one of the vectors for how these sorts of attacks that we might worry about would spread. And then another point, insider threat is not a worry when we start. If we build up a network with a bunch of volunteers who are helping people relay around, we're not going to have a huge government infiltrating the network and signing up half the volunteers at the beginning before anybody knows about it, before it is useful or visible. Okay, and then censorship is not uniform inside these countries. If you talk to a lot of people in China is the example I've been using, but there are lots of other ones. There are a lot of different ISPs, and each ISP, it's not like the government at the very top says, you will filter the following 47,000 places. They send down a very loose set of instructions. They basically say, don't embarrass us. And every poor guy at each ISP is left to say, well, what does that mean? What am I supposed to filter to not embarrass you? So each of them have to say, well, I guess probably not porn, and I guess probably not webcomics, and I guess probably not. And so each ISP ends up with a different set of things that they think they'd better filter. And that makes it a bit challenging to actually measure things. A lot of people say, well, what does the Great Firewall of China block? And at that point, the answer is, well, if you're in this province, it blocks this and this, and actually tomorrow it's going to block this because some guy thought it was a good idea, but the next day he'll change his mind and it won't block that anymore. So that's a bit challenging. Okay, another assumption we need to make, assume that the users aren't actually attacked by their hardware and software. There's no spyware installed, no cameras watching their screens, stuff like that. And that's a pretty challenging assumption depending on the country. I was talking to a group of dissidents from an East Asian communist country a while ago. And I was there to teach them all about security, and I was all set to say, 128-bit crypto good, 40-bit crypto not so good, let me tell you how these things work. And they were getting phone calls saying, so-and-so just got arrested. And they turned to me and said, our guy just got arrested, what do we do? And then I realized that I didn't need to teach them about security. They need some basic operational security. And that's maybe at a level that I'm not the best one for them to be talking to. They were explaining that, yes, Tor would be a fine solution, but when I go to the bathroom, somebody walks into my house and answers my Skype phone calls. There's a guy across the street with a parabolic microphone listening to every word I say on Skype. They steal my laptop and install stuff on it and give it back. That's a bad situation. I'm not trying to solve that one here. Maybe we'll get to that eventually. And then, similar to that, assume they can get a real copy of Tor. If Burma distributes the Burma version of Tor, and you go get that one instead and you install it, and it gives you away every time you do something, you never used my software in the first place, nothing I can do to help you. So maybe PGP signatures. I've got business cards up here that have the PGP key that signs the Tor source code, so at least you guys will know you're using the right Tor. But does that really help somebody in Uzbekistan that I've never met? Okay, so those are a bunch of assumptions and pieces of the threat model to try to give you some intuition about what we're talking about. So what do we have now? Tor gives sort of three different anonymity properties. The first one is somebody watching your local network can't figure out or influence what you're doing. They can't say, oh, Alice is connecting to CNN, I'm gonna react on that somehow. And that's clearly useful for blocking resistance. Another one is no single router in the path knows about both you and where you're going. And that means that the attacker is not as likely or as incented to sign up a couple of servers so that they can start linking users to where they're going. If we were just using a single hop proxy, then the attacker should really show up and say, well, I'm going to sign up half your network, and I'm going to learn all about the Alices who use it and all about the Bobs that they visit. That would be bad. And then the third anonymity property we aim for is the destination or somebody at the destination can't figure out where you're coming from. And that's maybe not as obviously useful, but it also means that they can't bust you. A little while ago, Yahoo, so the Chinese government went up to Yahoo and said, hey, there's this guy who's writing about stuff, and we'd like to know who he is. And Yahoo said, why, certainly. Here's his IP address. Here's his identity. Here's his mail. Here's everything that you might want to know about him. That's a shame. We'd like to sort of build a system that doesn't make that quite as easy. And then the other side of that, maybe they'll treat you differently. Maybe China goes to Google and says, anybody who's coming from China, even if they're going through this censorship system, please censor them for us, because otherwise we won't like you as much. We won't let you do business in our country, stuff like that. So there are a bunch of other things that Tor gives us right now, and I'm going to give you a brief overview of the ones that matter for the design I'm going to talk about later. One of them is we have a well-analyzed, well-understood discovery mechanism. We've got these things called directory authorities. There are 5 of them. Their locations and their public keys are hard-coded in the Tor that you get, so you know you're bootstrapping into the right network. They automatically aggregate all the Tor servers out there. They test them to see if they're up. They publish signed summaries of all the servers you might want to use. Clients go to either the authorities or any mirror, and they fetch a big list, and now they know who they can use. And this is important for anonymity reasons, that the clients get the same list. You don't want to have, well, I used this 40% and I used that 20%. You want all the users making the same sorts of decisions over the same sorts of input, or they're not going to blend together very well. Okay, so that's piece 1. Piece 2, the list of directory authorities, there are 5 that are put in by default, but it's not like they're hardwired. You can put in your own default. You can go to the configuration file and say, I don't want to use those ones that the Tor guys want. Here's my new set of directory authorities. And suddenly you're connecting, you have created a new Tor network. And that might be handy for all sorts of reasons. Maybe somebody could set up a separate Tor network in Iran or in Indiana or whatever sort of situation they might need one. On the other hand, you really don't want to have 50 different Tor networks out there, because then you're splitting your users up between a lot of different networks, which again is bad for anonymity. Okay, what else do we get? Tor automatically builds circuits. They're called paths. And it rebuilds them and rotates them, and it takes care of making sure that you've got a circuit up and available that will support whatever connection you want to do. So more broadly, Tor is just, it's a tool. You put in a bunch of server descriptors, and it builds paths through them. So you could get your description of what servers are around from the directory authorities, or you could get them some other way. We don't care. You tell us about servers, we build paths through them. I've been talking with a lot of community wireless people because we've got a tool that lets you build paths through whatever network you happen to have. and they provide TLS for free, and it's pretty easy to extend. So we're not just an anonymity system for the Tor network we happen to have built. We're more of a general purpose tool. And Harvard's project called Blossom makes this a little bit more concrete. They don't care about the anonymity properties of Tor. They care about the reachability properties. They want to say things like, show me CNN.com from Iceland, or show me the resource called the website from the location called Jeff's apartment. And at that point, Blossom will automatically build a circuit that ends at wherever you want to end, and it'll go to that resource. So this is another way of being able to look at the internet from different perspectives and get a better sense of how people in various areas of the world can see things. Okay, another feature, Tor separates the role of internal relay from the role of exit relay. So Tor servers have these things called exit policies. They specify which IP addresses and ports you're willing to connect out to. Some people say, I'll connect to anything. Some people say, my IT guy already hates me. I'm going to be a non-exit node, so he doesn't hate me anymore. And it depends a lot on what you want. So this means that we can have a lot more servers out there than we would if we demanded that every single server be an exit node. Okay, so this increased diversity is sort of where Tor gets its security, its anonymity, because having a lot more servers, as I described at the beginning of the talk, that's where our security comes from. The larger the Tor network is, the more diverse the servers are, the more likely it is that there is not an attacker who can be on both edges of the network. Okay, another feature, Tor is sustainable. We've got a community of developers and volunteers. They help out. They do all sorts of things. There's a question in the back. Yes? Is there? Yeah, so the question is, do you have enough exit relays, or do you have 5% exit relays and 95% internal relays? And the answer is we have about a third exit relays, which is about the right number because for 3 hops you want about a third of them to be exits. We'd rather have more, of course, because right now, since about a third of them are exits, we have to not choose the exit servers anywhere else in the path, or we're going to overload them. We're going to put more than a third of the traffic on them. So it would be great to have more exit nodes because then we'd end up having more possibilities for every choice, and that leads to more anonymity. Okay, so one of the interesting things about the anonymity world is periodically people say, I'm going to make money off this. I'm going to build an anonymity system, probably using a one-hop system, and I'm going to charge users to use it. And then we'll all get rich. They'll have their anonymity, I'll have a big startup. Typically, you don't collect enough money from these users in order to actually pay for your bandwidth, and it all goes bad. So we're more of a volunteer community effort where various people around the world say, I've got some extra bandwidth, this is important, I think privacy, security, anonymity, whatever you want to call it, is important, so I'm going to donate to the network. So our sustainability is rooted in the open design, the clear specification, modularity, open source. This means that we're more likely to be around later on as a tool that could be used for whatever people want to build out of an overlay network. Okay, and we've got a few 100,000 users all around the world. Ordinary citizens, activists, corporations, law enforcement, government, military. There's a group of Navy soldiers in the Middle East right now who are using Tor to connect back to their mail servers in Maryland. And they don't want anonymity. They really do want to authenticate to the mail servers in Maryland, but they want protection against an eavesdropper. They don't want somebody watching the house in Iraq to say, hey, I know what their affiliation